Good morning, all participants. It's interesting to see that today also we have more than 200 participants. Today our subject is lightning protection, but as all of you know, lightning protection is a big subject. We are going to exclusively touch upon some important topics which is applicable for high-rise building or large industrial building. So the contents of the presentation are from ISIEC 62305, or you can also say from the National Building Code 2016, internal and external lightning protection. Now, the first point which I wanted to tell you is the ISIEC 62305 is actually classified, it is a classified code of practice. Code of practice is a little bit above the standard as per the regulation of Government of India. Code of practice is a mandatory requirement which has to be implemented in every building. You can look at it in the regulation 12.2 of CEA, measures relating to safety and electric supply. So basically, ISIEC 62305 is a code of practice. Similarly, National Building Code is also a code of practice. So here I am a member in the TC81 of IEC, which is responsible for making standards related to lightning safety, lightning protection, and hazard prevention. I am in the ad hoc groups and maintenance team, which is mentioned there, MT14, MT21, working group 18, and so on. So with this introduction, let me start the presentation. As I said, I am not going to explain all about lightning protection. I am trying to be specific to some kind of challenges which we are facing every day, especially in high-rise buildings. The first one, what is this standard ISIEC 62305? It is actually adopted from IEC 62305, which is a standard used globally. All over globally, 62305 is the adopted standard, whether it is in Europe or America or whatever. Of course, the number may change depending upon the national things. For example, in America, they don't call it as 62305, they call it something else, but the contents and the principles are same. So basically, IEC TC81 makes the standards which is for global use. It consists of 4 parts. Part 1 talks about basics of lightning, analysis and threat analysis, how lightning can be harmful to you, what kind of solutions are possible, and so on. What kind of parameters you are supposed to take care. Similarly, part number 2, 62305, part number 2 talks about risk assessment. Risk assessment is a technique which is included in the standard. Based on various parameters, you can find out whether your building require lightning protection or not. If your building require lightning protection, say for example, a small building, a normal residential building, probably lightning protection may not be required. Whereas a large building, high-rise building, lightning protection may be required or is required mandatorily. So that decision can be taken by making a small risk assessment. Then, if your building require lightning protection is classified into 4 levels, level 1 to 4, 1, 2, 3, 4. The second question is, your building require lightning protection and what is the minimum level of lightning protection required? It is not to find out what maximum protection is required, but what minimum. That means whatever the money you are spending for installing lightning protection, it has to be economical and it has to be useful. That is explained in the part 2 risk assessment. Part 3 talks about external lightning protection. External lightning protection consists of air termination, down conductor, earthing, and shielding. Air termination at the top of the building, how you are avoiding a direct lightning strike into the building. Second one, how safely you are carrying the lightning current from top to bottom of the building. The third one, earthing, how safely you are dissipating the current to earth. Shielding, how safely you are avoiding some kind of spark overs and so on. The part 4 talks about protecting the internal parts of the building. Here the subjects are equipotential bonding, surge protective device, bonding and shielding, cable routing, and so on. So there are several subjects, there are several components which has to be taken care if you install a lightning protection. And today's subject, we are going to discuss external lightning protection. That means protecting a structure, means a building, and that itself a high-rise building. So I have to be specific on that particular subject. Otherwise, lot of lightning protection to explain it completely probably take 2 or 3 days. So this is the reason I wanted to be specific. When we talk about lightning protection, two theories are explained in the standard. One is the lightning protection level, and the second one is the lightning protection zone, lightning protection zonal concept. In fact, the zonal concept is not only derived from the lightning protection standard. Zonal concept is derived from all the electrical safety, from the basic safety onwards. A kind of zoning has been carried out. When you look at lightning protection, always people ask, what is this 10 by 350 microseconds? The energy content of lightning has been generated in a laboratory as a wave shape. Finally, whatever the components which we are using need to be tested. For that testing, we need to have a standardized energy form so that all manufacturers can be at the same level to do the test. And that kind of energy, equivalent energy, has been created in the form of a current wave shape as 10 by 350 microseconds. Means in 10 microseconds, the current, probably 100 kiloampere current from 0 to peak goes in 10 microseconds, and it comes to half value in 350 microseconds. So basically 10 by 350 is an equivalent wave shape, current wave shape of a lightning strike. Don't think that lightning always will be 10 by 350. It is not like that. This 10 by 350 is an equivalent representation of the energy contents of a lightning in the form of an impulse current. There is one more impulse current or one more wave shape which we always refer, which is called as 8 by 20 microseconds, where I am showing it in the green color. 8 by 20 means the current goes from 0 to peak in 8 microseconds and come to half value in 20 microseconds. Generally, 8 by 20 is used for testing, or it is the standardized wave shape for testing surge protective devices and some kind of components which is used in lightning protection system. Now, two subjects which you should understand is components of external lightning protection. Means you have a building, you have some clamps, clips, conductors. Those need to be tested with 10 by 350 microseconds wave shape, and the smaller devices such as SPDs, sometime 10 by 350 microseconds, which is called as type 1 SPD. Sometime the SPDs are tested with 8 by 20 microseconds, which is called as a type 2 SPD. So basically there are two energy wave shapes. Risk assessment, the second part of the lightning protection, the ISI 62305 part 2, risk assessment. Risk assessment is a technique with which the risk involved in a building has been calculated. Say, for example, depending upon the place where your building is located, number of thunderstorm days per year, size of building, type of service, number of people, and criticality in case of failure at one side. And then the standard gives you a kind of a tolerable level. Tolerable level means up to what level you can have safety. For example, for human safety, 10 to the power of -5, in the sense, out of 1 lakh lightning strike, 1 can be harmful to human being. For protection of electronics, 10 to the power of -3 means out of 1,000 strikes, 1 can be harmful to electronics. So based on the tolerable, compared with the tolerable limit, on one side, and on the other side, the minimum cost which has to be spent for lightning protection, we are making a kind of an assessment and find out, first, number one, whether your building require lightning protection or not. Number two, what level of lightning protection is required if LPS is necessary. Now, please understand that risk assessment for a larger area, a larger village, town, district, all these are not possible. Why I mentioned this is there are some articles which we are reading nowadays. People claim that village level lightning risk assessment has to be made. district level lightning risk assessment has to be made. All these are actually not possible. Risk assessment is made for a typical structure or a typical building, just to find out whether lightning protection is necessary or not. If necessary, lightning protection is classified into 4 levels. Level 1 to 4, depending upon the current. For example, level 1, 2.9 to 200 kiloampere. Level 4, 15.7 to 100 kiloampere. So 4 levels. The purpose of the finding out the level is to find out how much, whether the money you are, the economics which we are spending or the cost which you are spending, whether is it worth or not. That is a simple method. Now, how lightning protection looks like in a typical building. I'm just showing you. Some of you probably already knows this particular picture because this typical picture I always refer. Imagine you have a building with a flat roof. The first job is to make an air termination. I have made an air termination here as a grid. There are 3 methods: a rod, vertical rod, or air termination mesh, or catenary wire. The third method is catenary wire. And there is a technique which can be applied to find out the probable place of lightning strike, which is called as a rolling sphere method. Rolling sphere will not protect a building. It's not a material. It's a technique which has to be applied to find out whether the air termination is able to protect the building or not. So basically, in a simple way, on a flat roof building, the recommended practice is to have a mesh. Let's say, for example, I have made a mesh and there are some electrical items which is coming, like a solar PV, an air conditioner, chiller, which is above my mesh. In that case, what I should do is I have the option of making equipotential bonding, and probably I have the option of making some rod near to the solar PV, maybe 2 rods near to the solar PV and 2 rods near to the chiller, so that these rods avoid the direct lightning strike into the chiller. This is a typical case. For example, I made a grid of 15 by 15 meters, few rods to protect the roof mounted air conditioner and solar PV. Equipotential bonding with air conditioner and solar PV has been made at the top of the building. This is a typical case. So a mesh, some rods, everything interconnected together. This makes the air termination system. The second part is down conductor. As I said, rolling sphere or the electrogeometric sphere is used to design or used to position the air termination system. Air termination is not a protecting technology or protecting technique, like it's not a component. It's a technique to find out the probable place of lightning strike. The second part is down conductor. In the picture, I have put some dotted here, some dots. It is just a representation that there are 10 down conductors in this particular building. So 10 dots means from the roof, we look at 10 down conductors on the building. The first point of this down conductor is number of down conductors specified in the standard. Number 2, if you require 10 down conductors, these 10 down conductors must be placed outside the building, all around the building, on the periphery of the building. It has to be equidistant if possible, or the minimum distances which is mentioned in the standard must be maintained. Say, for example, 10 meter between, minimum 10 meter between each down conductor, or sorry, maximum 10 meter, or an average 10 meter between down conductors. So in this typical case, we have, let us say, for example, 10 down conductors. You can see the building at the top, there is a mesh and there are 10 down conductors, and these particular down conductors, each of the down conductor has to be connected to an earth termination system. What is an earth termination system? It consists of an earth electrode, because whatever the current coming from the top due to a lightning strike through the down conductor has to be dissipated to soil. So there are 10 earth termination system or 10 earth electrodes in this particular case. So you have the air termination, you have the down conductor, and you have the earthing. The fourth subject, which is of equally importance, is equipotential bonding. What is equipotential bonding? You can see the down conductor is connected to MET. MET is nothing but the main earth bus bar of the mains incoming panel. Down conductor must be connected to the electrical system, protective earthing of the electrical system, and an equipotential bonding has to be made. Now, when we talk about equipotential bonding, down conductor and the earth bus bar can be directly connected. But this earth bus bar and the phase and neutral conductor has to be equipotentially bonded through a device which is called as SPD, surge protective device. So basically, your lightning protection consists of an air termination, a down conductor, a earth termination, and an equipotential bonding system consisting of SPDs. Now, this kind of vertical electrodes, one of the technique which has been an improved version of earthing system is called as a type B earthing. Probably you can see here all the earth electrodes are interconnected together. One of the technique which is included is the ring earth. That means you make a earth electrode all around the building as a ring. That is more efficient than putting individual vertical or horizontal earth electrodes. So type B ring or foundation earthing, more advantageous for a critical building or a high-rise building. So basically your lightning protection consists of air termination, down conductor, earthing, and SPD. Now we go to the next most important subject, which is more appropriate or more applicable for buildings of a higher height or taller buildings or buildings of larger size, such as an industrial building, which is length and to breadth. Probably length is 100 meters, breadth is 50 meters. And so for such large buildings, we are also supposed to calculate the separation distance. Before that, we have to make a decision: electrical separation or bonding. What is electrical separation? Electrical separation means separation distance required at top floor between electrical wiring, metal frame, and from the down conductor. Say, for example, electrical separation. It means the parts of lightning protection system must be separated, physically separated, electrically separated from the structural parts of the building. I have better pictures. I will show you. Always the separation distance is calculated with equipotential bonding at the ground floor. Here you see with equipotential bonding, in the sense the down conductor and the electrical system are equipotentially bonded. Now, how to calculate the electrical separation or electrical separation distance? So, as I said here, there are two techniques. One is electrical separation. Next one is bonding. It means you make equipotential bonding everywhere. First, let us look at what is electrical separation. Electrical separation means at the roof you have the air termination, then you have the down conductor, and at the bottom of the building you have the equipotential bonding. Equipotential bonding. Now, the parts of air termination means the air terminal, the grid at the top, and the down conductor. Technically speaking, if you are adopting the technique of separation, then you have to calculate the separation distance, yes, and keep the air terminal and the down conductor physically away from the building. Away from the building, away from what? Away from frame of the structural steel, away from electrical wiring and apparatus, away from rebar, away from metal doors, away from metal continuously connected metal doors and windows. So basically, in order to avoid the flashover, say for example, a lightning is hitting this corner of the building, due to the surge impedance of the down conductor, there can be a flashover from the air termination to the building, or something like this. There are several flashovers at several locations of the building. In order to avoid flashover, technically, we are keeping the air termination and the down conductor physically away from the building at a separation distance. Yes, so it's very easy to understand. Now, how the separation distance is calculated? There are constants. For example, depending upon the level of lightning protection, 1, 2, 3, 4, the constants are given in the standard. Depending upon the insulating material, air or concrete, wood or brick, the materials are given. You always select the most unfavorable material. For example, next slides you will see how this has to be done. Then The coefficient, like the number of down conductors, one down conductor, two, three, and more, these constants are always given in the standard with some notes. Please have a serious look on that. With those standards, I'm just trying to find out the separation distance of in an RCC building where I'm going to make an external lightning protection system, a level 2 lightning protection. Height of my building is 35 meters, length 30 meters, width 25 meters. Just as an example, you think that it's a 10 floor building, 3.5 meter each. I'm going to make an external lightning, or I wanted to make an external lightning protection system with equipotential bonding at the bottom. I'm trying to find out the separation distance. So these, if we take the values from the constant, S equals Ki divided by Km into Kc into L. L is nothing but the distance from the top of the building up to the equipotential, the height of the building in this particular case, that is the L. If we calculate the separation distance required in this kind of a building, a 10 floor building, is about 0.924 meters, almost 1 meter insulation is required in air, almost 2 meter insulation is required in case of brick or concrete. And this is with equipotential bonding at the bottom of the building. Now, if you don't have the equipotential bonding at the bottom of the building, the separation distance is really unknown. It may be several meters. Now, the question is, when you do lightning protection, are you making this equipotential bonding? You are making an exposed lightning protection system. Are you making the equipotential bonding? In India, unfortunately, a lot of buildings, the equipotential bonding do not exist. Under that condition, please note that the separation distance would be very, very high. It is actually practically what can happen is there can be flashover at several points of the building. Now, what does the same calculation I am making for a building of height 70 meters, lightning protection level 1, 20 floors building 3.5 meters each with equipotential bonding. Under that condition, the separation distances are 2.64 meters in air and 4.92 or about 5 meters in brick. What does this mean is the air termination mesh and the rod and parts of this down conductor. See, at the bottom you have equipotential bonding. Away from the equipotential bonding, the distance increases, and at the roof of the building, a distance of approximately certain meters are required between the air termination or between the parts of lightning protection system and the building material. How far it is? 1 meter separation distance for a building with a 35 meter height, level 2, the previous case which I explained. 2 meters for, if we look at the separation, the insulation material is actually brick, not air, brick. 2.5 meters air if your building is 70 meters height, 5 meters if your building is 70 meters height and the insulating material is brick. Insulating material is nothing but you see between the air terminal and the down conductor, you have to put some support. And if that support is brick, or if the distance which we are calculating from the air terminal to the metallic part, if the separation is physically by brick, you need almost 5 meters for a 70 meter building with lightning protection level. This means the air termination system in the last case has to be 5 meters away from your RCC building. Just imagine, is this practically possible? Practically, keeping air termination or down conductor away from the building is very difficult. You need to make a 5 meter maybe FRP support, and you have to make the mesh above the building, 5 meter above the building, on the side 5 meter away from the building, which is practically impossible. Now, when it comes to, this is what is explained in the 62305. Now, once when we explain this subject to the construction site or to the clients, most of the clients say that, no, this is not required, you leave it. We don't want to calculate the separation distance, or we don't want to consider separation distance. Please note that if you don't consider separation distance, your lightning protection system is inefficient. lightning may hit the air termination, but instead of the current flowing through the down conductor, there will be flashover between the air termination to the metallic parts of the building. As a result, current is going to flow through your building, which may destroy so many things. The second claim, a lot of high-rise buildings in India are using non-standard air termination called as early streamer emission system in India. All of you knows very well. One rod, one down conductor and one earth electrode. In large industrial building, again, one rod, one down conductor and one earth electrode. What is this down conductor? It's generally 90% of the cases, it is a 70 square millimeter insulated copper wire. What is the claim? These manufacturers claim that one rod protects 100 meters, and finally the claim is it is as per the French standard, NFC 17102. If we look at the French standard is not explaining ESE as a one rod, one down conductor and one earthing. It is explaining a proper equipotentially bonded, a proper lightning protection system consists of several components. So basically, the French standard is similar, I would say, over and above IEC 62305, you are making some more arrangement. If you read the NFC standard, it explains lightning protection as you make a Pakka lightning protection system as per 62305, and over and above, you make some additional arrangement like a ESE air terminal. That means the story, which is the propaganda which is made in India, one rod, one down conductor, one earth electrode, is absolutely wrong. This is never written in the National French Code. Now, anyway, our subject is not only that. Our subject is separation distance. In the same French Code, you can find the separation distance calculation. Say, for example, clause 5.6, separation distance S equals Ki divided by Km into Kc into L. The same calculation which is included in the IS IEC 62305. In the NFC standard, you can also find this kind of a picture. What does it mean is the down conductor, you keep equipotential bonding at the bottom of the building, and you see here the air terminal and the down conductor separation distance, yes, approach limit of metal element. That means the metal elements of the building must be away this much this much distance from your building. The same technique of IS IEC 62305 is included in NFC 17102. But my question to the clients or the people, those who are using ESE, I'm sure you must have never considered this particular point. Of course, in the conventional lightning protection or as per 62305, also in most of the cases or in some cases, clients ask to neglect separation distance, but we always oppose this and we sometimes reject the designs or we sometimes don't offer any solution to them if the separation distances are not calculated. Now, please understand that the same separation distance is applicable for lightning for an ESE standard, NFC standard as well. Now, if we apply the same separation distance, you can find the same values in also as well. If we apply the same separation distance for building number 1, 35-meter building with equipotential bonding, so you get a value of 2.1 meter. The separation distance required for ESE rod is double than the normal thing. In brick, again 4.2 meters. 70-meter building, the calculation says about 5.6 meter and 11.2 meter away from the building. What does it mean? It means the ESE rod and the down conductor has to be the separation distance in the typical Indian way, one down conductor. In that case, the separation distance required is 2.1 meter for a 35-meter building with a level 2, almost 11.2 meters for a 70-meter height building with LPL 1, where we consider the separation material is brick. So much distance away from the building. That means if you look at the actual scenario, 70-meter building, the air termination and the down conductor has to be physically away from the building. How much physically away? 11.2 meters physically away from the building. That means you have to have some kind of or isolated or insulated material between the red line and the building. Red line is nothing but the parts of lightning protection. And the distance keep on reducing once when we reaches towards the bottom, for example 5 meters, and at the bottom of the building 0 meters if equipotential bonding is made. If it is not made, of course all these calculations are wrong. In an industrial building with hundreds of meters long, then the distance is something like this. You have to have an insulator here 11.2 meters, another insulator probably 5 meters. So basically the air terminal and the down conductor has to be kept away from the building 11.2 meters away from the building. This 70 square mm wire insulation, 1.1 kV insulation, has nothing to do with this 11.2 meters insulation. 11.2 meters insulation is a large insulation. The spark over voltage, or the voltage which is going to create due to the surge impedance of the cable, is very high. This also means the lightning current flowing through the conductor to the down conductor can make a flashover up to a distance of 11.2 meters. So basically, the separation distance calculations are very much included in the building. This is mainly applicable for large buildings. You see, for smaller buildings, this is not very much, or the distances are quite less, because the length of the equipotential here, the length I am showing on the cursor, 70 meters. In a normal building, probably 7 meters. Then the calculation changes. So this is actually a challenge. Whenever you do lightning protection, please always keep in mind lightning protection is not only about air terminal, down conductor and earthing and SPD. It is also about the separation distances if the technique implemented is an exposed, isolated lightning protection system. So now what is the solution? The solution is the clause 6.3.1 of IS says, in structures with metallic or electrically continuous connected reinforced concrete framework, a separation distance is ignored or not required. What exactly it is? You see, yes, the standard is made for different kind of construction for the global use. In some countries, Europe and America, even today, the wooden constructions are followed. Different techniques are there. Predominantly in India, for large buildings, we always use RCC or PEB. So this clause, what it says is, in structures with metallic or electrically continuous connected reinforced concrete framework, separation distance is not required. That means RCC buildings, separation distance is not necessary if you make use of it. In PEB building, separation distance is not necessary if you make use of it. For that, what you should do? Use of natural component. What is natural component? Natural component made of conductive material which will always remain in or on the structure and will not be modified. That means the material which is used for construction of your building, such as interconnected steel reinforcement, metal framework of structures, etc., may be used as part of lightning protection system. That means the reinforcement and metal framework. So other natural components can only be considered as being additional to LPS. What is the other natural component? For example, you have an aluminum facade. The frame of the aluminum facade has to be considered as an additional thing. It is not a steel reinforcement. It is not a complete metal framework for the structure. Metal framework for the structure, what the standard mean is the column itself is steel, PEB building. So your aluminum frame has to be considered as an additional thing, not as a down conductor or so. Now, how to make a building with natural component? What you are seeing in the picture is a building with RCC. It's a RCC building, maybe several floors, multi-floor building. At the top of the building, you have the air termination, which is always exposed because lightning must hit the air termination. And probably some covering for the parapet. I have taken the picture from the standard. That is why actually in India we don't have the habit of covering the parapet with this kind of a conductor, but we have the habit of handrail on the parapet, metallic handrail on the parapet. If you have a metallic handrail on the parapet, the metallic handrail will do the job of air termination. Then the black color line, which I have changed to red, means an additional conductor embedded inside concrete. It's an additional conductor embedded inside the concrete. Now you have item number 6, which is basically some kind of equipotential bonding connections. Please understand that this is a typical picture. Each of these component has to satisfy its requirement. There are several technical requirements. It is not like you put a conductor from top to bottom of the building and your job is done. It is not like that. So basically, item number 9, steel reinforcement in concrete with superimposed mesh conductor. So basically, for high-rise buildings and buildings with or buildings of larger size, separation distance is very difficult to calculate and maintain. Basically, calculation is possible, but maintenance is very impossible. The best method is use the naturally available steel as a part of lightning protection system. For example, in an RCC building, you can put an additional conductor embedded, superimposed in the reinforcement, and this particular conductor will support your structural steel in performing the whole building as a lightning conductor, for example. Now, in this particular case, the down conductors and the earth electrodes or the foundation earthing is not exposed. It do not affect the aesthetics of the building, and it is most efficient for electronics, because what happens, whenever there is a current flow through the structure, the amount of current, the current is splitted to several hundreds of routes. As a result, concentration of current through one specific conductor is less, because the current is going to flow through the entire building. As a result, the effect of the current flow with a large di by dt rate of change of current is reduced, and you get maximum protection for your electronics. Now, how the performance of this natural component is carried out? It is carried out by making a continuity resistance test. Continuity resistance test, I'm sure all of you are aware. The important point is you are supposed to make this test with a meter of minimum 10 amps current. I have seen in a lot of places the normal earth electrode testing meter is used for this particular purpose. Actually, it won't work. Even there are meters like the meters which is used for testing the earth pit resistance, the Werner method, 4-pole method, 3-pole method. Those meters are used for this particular testing, but please understand that it won't work. The minimum requirement is the meter which is used for this testing shall have a test current of minimum 10 amps. Anything higher than 10 amps test current is necessary, and the resistance from the one part to the bottom, top to bottom, shall be lesser than 0.2 ohms, 200 milliohm. So this is how the performance is ensured. Now, when it comes to this, embedding or using natural component, we face a lot of challenges. The first one, if you read the standard is allowing materials such as copper, stainless steel, copper bonded steel, MS means a bare steel conductor, galvanized steel. All these materials are allowed. But usage of each of these material, some specific recommendations are also made in the standard. Similarly, the standard also recommends, or in the picture, it also included to use the rebar itself. You use the rebar, you can use an additional conductor such as copper, stainless steel, copper bonded steel, MS or GI, or you can also use the rebar itself with some kind of special clamping, special welding and so on. But the standard also had recommended like this. In order to avoid confusion between different type of steel rod in concrete, it is recommended that a round steel rod of at least 8 mm diameter with a smooth surface be used as additional conductor in contrast to the ordinary ribbed surface of the reinforcing rod. So what the recommendation is, it is recommended, please read, it is recommended. If in a standard, if the word recommended is used, That means the standard is recommending to use. The standard is recommending you can use the rebar, but the standard is recommending to use a conductor with smooth surface. That means a conductor of copper, stainless steel, or whatever the material with a smooth surface as an additional conductor in the concrete is recommended in the standard, which is preferred favorable, or it is preferred more than the ribbed material. Number two, what kind of material which we use? Whenever it comes to the type of material, we always talk about galvanized steel. All of you knows GI, which is available very much abundantly in India. Now the recommendations in the standard table 5. Galvanized steel may be corroded in clay soil or moist soil. That means the galvanized steel, if you use a natural component, imagine you are making a grid under the building and your building has to be there for next 100 years. And if the galvanized steel GI strip or GI conductor which is put under the building, if it corrode within 10 years or within 20 years or within 30 years, after 20, 30 years, you have nothing on the ground. So you will be in deep trouble. So galvanized steel may be corroded in clay or soil, in moist soil. So while using natural component, you have to double think about using GI. Galvanized steel in concrete should not extend to soil due to possible corrosion from steel just outside the concrete. I have a picture I will show you. Galvanized steel in contact with reinforcement steel in concrete should not be used in coastal areas where there may be salt in groundwater. You see, one technique which is used is foundation earthing. If you look at the explanation of foundation earthing, is the conductor is inside concrete and the concrete or the RCC floor is in soil. It is called as wet concrete. A concrete or an RCC which is in soil is often called as wet concrete. That means it has got some wetness and the resistance of that concrete is approximately 100 ohm meter. That is what is specified in the standard based on several studies. So these recommendations are made. The last one, galvanized steel in contact with reinforcement steel in concrete should not be used in coastal areas, because if you put GI inside the concrete, GI will it will corrode faster. So GI cannot be used in soil because of corrosion. GI cannot be used in coastal areas or in places where you have salt water. You will be in trouble. And these comments you are supposed to read and understand it. In the clause E 4.3.4 materials, the behavior of galvanized layer on steel in concrete is very complicated. I will just read the explanation or which is highlighted. Galvanized steel should therefore not be used in coastal areas and where there may be salt in groundwater. That is one point. The second is, as the use of galvanized steel in concrete require evaluation of many external factors, this material should be used only after careful analysis. So using GI for this purpose inside concrete has to be carried out after careful analysis. But unfortunately, nowhere it is written what careful analysis. So it is very difficult to make to find out an answer for this careful analysis. The simple method is don't use it. With this in mind, the use of other mentioned material is preferred over the use of galvanized steel. The standard has recommended very clearly that GI, if you put it inside concrete, is having certain problem. Either you analyze and do it if you can, preferably use the other material over galvanized steel, because galvanized steel is a problem. Now, further, these are the further classes. For example, galvanized steel outside the concrete in contact with reinforcement steel may under circumstance cause damage to concrete. What does it mean? You have the building here. Now, item number 10, we are taking a connection outside from the concrete to do something in soil. And if you are using galvanized steel in this soil, it will be forced for accelerated corrosion. Galvanized steel will disappear within few years, within few months. So galvanized steel electrodes in soil should be connected to the steel reinforcement in concrete by isolating spar gap. That means here a direct connection in the soil would significantly increase the risk of corrosion. Isolating spar gap should be used. So for example, what it says is, If you wanted to connect, you have a natural component used as down conductor, and you have to connect to something which is in soil, and that something is galvanized. Don't connect directly is the recommendation. You put a spar gap in between. So electrical isolation or spar gap is necessary. So these recommendations are there in soil. Why I am very specific in this particular case is whenever we go for or whenever we design, always people try to mention that use GI because GI is cheap. Use MS because MS is cheap. So GI, these are the challenges. Other case, people always try to use, instead of, the first recommendation is you use your MS conductor, the rebar itself. The standard says to use an additional conductor with a smooth surface. The second recommendation from the client is then you use a bare conductor. That means you use a steel conductor, round, smooth surface, but without any coating. In this case, out of our experience, what we are facing is after finalizing, after making this installation, we are supposed to check the continuity resistance. In several cases, the continuity resistance check is failing. Using MS is having that particular risk. Sometimes the required resistances are not possible, probably due to the corrosion or the kind of the joints are not proper and so on. So MS material is also having a risk. Please understand that after casting your steel or after construction, you cannot change anything. So if you wanted to make some modification, impossible. Now, designing of air termination, let me skip it. There are several techniques for designing the air termination, which is the techniques are called as the mesh method, the protective angle method, the rolling sphere method. Not very important for this presentation. Let me skip it. Challenges. The challenges which we use or which we face in every installation is most of the time when we get the drawing, the construction is already over. The structure is already over. And then they ask to make a design. And once when we tell that, sir, there is an important subject called separation distance. You have to keep your air terminal 1 meter away from the building or 2 meter away from the building. Nobody allows it. Then people always say, the other challenge, the roof mounted apparatus, because when we get the drawing, most of the time the roof is empty. But later we came to know that there are so many things coming up. Chillers are coming. The facade cleaning rail and its associated equipment are coming. That means your probably the parapet you cannot use because something else is going to come. Roof mounted apparatus are unknown. Then in PEB buildings, the one of the biggest challenge which we always face is the usage of screws. Don't use any screw, don't put any hole, use some kind of sticking material, adhesive material. So you, with an adhesive, you connect your conductor holders into the RCC. Please understand that these adhesives have certain life, probably 5 years or 7 years. After 7 years you have to replace it. And more than that, by using adhesive, you are isolating lightning protection, and in case of any strike, there will be spark over across the adhesive tape. So that means the effectiveness of lightning protection is gone. The second challenge which we always face is the down conductor. Down conductor in large multi-storied buildings, if we say that down conductor has to be outside the building, then the first answer is no, no, no. That part of the building there is glass facade, this part of the building glass facade, so it will affect the aesthetics. You cannot do that. You route all the down conductor through one side of the building. So all the three sides are glass. You cannot touch that particular part. Your whole lightning protection down conductor has to be routed through one side. Practically, this is a violation of the standard. Your lightning protection system will not work. The second case, there is no space to route down conductor. Third case, multiple down conductors in one route. All these are actually violation of the standard. And then in some cases, architects are providing a dedicated shaft for down conductor. So I have 3 down conductors. You have 15. You require 15 down conductors, and all the 15 down conductors as group of 5, you take through 3 shaft. That is also not possible. If a typical building require 10 down conductors, all the 10 must run outside the building, preferably all around the building is a must, as straight as possible. So routing the down conductor through the dedicated shaft is also practically not possible. It is a violation of the standard. Then when it comes to earthing, most of the buildings doesn't have any space. There is no space, no soil, because the entire thing is probably we have to buy some land from the neighbor to put an earth electrode. This is the situation. We are always forced to keep earth electrodes far away from the building, which is also a violation, because if you keep it far away, as I said, due to surge impedance, the potential differences will be very high, or potential differences will be higher and higher. The last challenge is a lot of clients are always attracted towards the chemical earth. People think that chemical earth is a savior, and without chemical earth, if I say that I don't use chemical earth, then people say, aha, you are a cheap supplier. I will go only for a very big supplier who supplies chemical earth. So please understand that the story of chemical earth is not for our normal application. I will show you after the presentation. I will show you how this is written. Chemical earth is required for places where you have soil resistivity more than 3000 ohm meter. I will show it at the last. So basically, going to the conclusion, what exactly is required is the best solution can be made by using natural components, especially for high-rise buildings or large industrial buildings. Use natural components as much as possible. For example, in air termination system, on the parapet you make a handrail with an MS pipe, or with a pipe or a square material. You make a handrail. Your handrail will be a permanent structure, and the handrail will work as a air termination system. You must interconnect the handrail with the structural steel, something like this. The handrail must be connected. So use the handrail, which is an efficient way. Structural designs, lot of buildings have got structural designs, like some architectural design steel materials at the top of the building. We are sometimes forced to keep a rod over and above this structural design, which is practically not required. If your structural design is a steel material, that steel material can work as air termination. A small paint above the steel material you can ignore, which is also written in the standard. This small thickness of the paint, we can ignore it. Basically, the structural designer material, you can see if you look at the high-rise buildings, most of the high-rise buildings have got something at the top with some kind of design for aesthetics. So those materials, if they are made of steel, that can be used as air termination. This is one. Number two, down conductors. It can be embedded inside concrete. You put an additional conductor, not MS conductor, not you don't use the rebar, because these two are major challenges, which is these recommendations are made in the standard. Not galvanized steel. Better you use copper or stainless steel or copper bonded material. 3 materials can be used, which is not having any side effects. Then you can also use the PEB columns. Nowadays, a lot of high-rise buildings are with the PEB columns, steel columns, that also can be used. Similarly, for earthing, the best method is use the foundation earth. What is foundation earth? Here you can see in this particular case a building with you can see here the green color line, which is nothing but a conductor which is embedded inside the concrete foundation of the building. That will do your earth termination system. So this particular use of natural component also can be used for applications such as transformer DG. Our typical method is to transformer neutral to earth electrode, transformer body to earth electrode, DG to earth electrode, UPS separate earth electrode, lift separate earth electrode, and all. Actually, those method which we use for separate earthing of transformer DG UPS, of course it is a wrong method. The best and the recommended method is you make use of the natural component, but please understand that the company or the person who is designing, he has to be skilled enough to understand and make a design appropriately. Electrical system also can be integrated in steel structure when it comes to lightning protection. I'm sure that a lot of engineers already, or they always believe in ESE lightning protection system because of the propaganda. Now, please understand that lightning protection and earthing is a subject which actually require a lot of skill, but more than skill, the way it is explained by the salesman is given always. People are the propaganda things are always trusted. Don't go behind the propagandas, please. Download these standards, all the informations are there and you can use appropriately. Now, when it comes to the earthing of DG, UPS and the electrical system, you can also use the natural component. This is explained as TNS system with PME in IS 3043. Across India, we have designed and executed and tested probably more than 100 buildings, large size multi-storied buildings, large size industrial buildings with this technique where there is no earth electrode in soil. The transformer neutral is connected, transformer body is connected, DG is connected, UPS is connected, lift is connected, your electronic installations are connected, DMS is connected, everything integrated into the natural material, and that is the best and the recommended method which is included in the IEC standards. Not now, probably for the last 20 years. We are a little bit late. After the introduction of the national NBC 2016 National Building Code, the civil engineers started accepting this particular system. So the best way of making lightning protection and earthing is, especially for large buildings, high-rise buildings or industrial buildings or modern buildings, please see that there is a subject called separation distance, which is practically very difficult to maintain in a large building. The best way is to use the natural material or everything integrated into the structure. This is what I wanted to explain today's presentation. With this, I would like to thank you. We can go for a question answer. You can find out the videos of all our programs in both the websites, vidyutsuraksha.com and solvelv.com. Lot of information are there. Now, at the last, I would like to show you I told that I will show from the IS IEC 62305 how to make the chemical earth. What is the parameters of chemical earth? I am just on the IS IEC 62305 standard. You can see here 62305. I am just searching 3000. One moment. So here is the table. You can find this particular picture in the standard. Here you can see the section is 5.4.2 or 5.4, earth termination, how to make earth termination. Now you look at the particular picture, up to 3000 ohm meter is shown. Now you read the note here. Reduction of earthing resistance by extension of earth electrode is practically, several techniques are there. One of the technique is extending the earthing conductor in the soil, practically convenient up to 60 meter. In soil with resistivity higher than 3000 ohm meter, see, the wording is very clear. In soil with the resistivity higher than 3000 ohm meter, the use of type B earth electrode or earth enhancing compound is recommended. So more than 3000 ohm meter, two techniques are there. One is type B earth electrode or earth enhancing compound is recommended. Now practically in India, most of the places in India, we have soil resistivity probably 100 ohm meter, 30 ohm meter, 50 ohm meter, 200 ohm meter. For that soil resistivity, of course, the earth enhancing compound is not necessary, and earth enhancing compound only will accelerate the corrosion. So with this, I would like to stop the presentation and probably we can have a question answer session.